Thanks a lot, Paula, and thank you for the opportunity to talk in this workshop. So I'm going to be talking, maybe following up a little bit on the presentation that Monica gave about the interface between autonomous vehicles and public transit. So to get started, I'm going to show you this thought experiment that a group at MIT did, where they said, what would happen if you replace the 800,000 passenger vehicles in Singapore with 300,000 shared autonomous taxis, right? And so this visualization you see is a map of Singapore. Each of these nodes is a station for demand. The red dots that are moving are empty vehicles moving in the network, and the blue dots are vehicles with passengers moving on the network. And you see the time is about 12 o'clock right now. There's a lot of movement going on in the network. We saw the morning rush hour, and now we're going to start seeing the evening rush hour. And the disks that you see growing, the size of the disk is corresponding to the amount of time people are waiting. So now you see the industrial areas, the business districts, people are waiting for rides. Red streams or dots are moving to those nodes, picking up people and taking them back to their residential areas. Now, what this study showed was that you could serve this 800,000 passenger vehicle demand with about 300,000 vehicles, and that at peak waiting times, people waited only about 15 to 20 minutes. Okay. Now this is pretty nice. You, instead of 800,000 cars, you now only use 300,000. But the one thing I want to bring your attention to is all of those red dots that were moving in the screen, right? If these trips were taken using the 800,000 passenger vehicles, none of those red dots would have been moving in this simulation, right? So this is sort of to highlight the fact that whenever we have these, for example, ride-hailing system, be they autonomous or not, there is an increase in the total vehicle miles traveled compared to personal vehicle ownership, right? And this leads to increases in the negative externalities associated with that, such as congestion and emissions. And one other thing to note here is that when you have a city where multiple ride-sharing providers or ride-hailing providers are providing service, the market is fragmented. And because of that, the amount of distance that a vehicle needs to come pick you up or rebalance, as it's called, can increase. Now, what about autonomy? Right, so autonomy, of course, has the advantages that increased safety can lead to fewer accidents and better, more efficient movement through the network. We've seen a lot of talks on how autonomy can improve traffic efficiency. So not just fully autonomous, but even connected vehicles through things like flow smoothing. And also we have the potential for increased accessibility, right? Which is also a good thing that's desirable in transportation networks. And in fact, we should be a bit careful about using vehicle miles traveled as a metric for lowering vehicle miles traveled as a goal, because lowering vehicle miles traveled shouldn't be a goal. More vehicle miles traveled, if it's for good reason, is good. We want people to have increased access to personal mobility, right? So the real metric we should care about, I'm going to claim, is the ratio between vehicle miles traveled and personal mile traveled. So for example, you want to increase in vehicle miles traveled is okay, but an increase in vehicle miles traveled per passenger mile traveled is not okay. And as you can see from the simulation I just showed you and this graph from some data related transportation network companies, is that in these types of services, this ratio can go in the wrong direction, right? So let's look at this graph in a little bit more detail. So this is ride-sharing data is notoriously hard to come by because these companies, for many reasons, are not that interested in sharing this. But there was a study done last year by a group that got data from Uber and Lyft for a number of major metropolitan areas. And they looked at how many miles were traveled in the system in three different types of categories. So the orange at the bottom is the miles traveled while the driver is waiting for a ride request. So you can think of these as the vehicles just idling around, moving to locations where they think there might be passengers to pick up, coming from wherever they live to a city center. So a lot of drivers coming from suburbs or outskirts of the city to a downtown area to get riders. So that's the orange. The P2, the area that's sort of a dark green, is the amount of miles driven when the vehicle has been assigned a request and is going to pick up that request as an empty vehicle. And the purple at the top is the actual amount of miles that these vehicles are driving with passengers on board, right? Now, as you can see, about 40% of the time is spent without a vehicle, without a passenger on board the vehicle, right? So this again speaks to, through data, the point that I was trying to make. Now again, we talked about some advantages with autonomous vehicles, but there are also disadvantages where, due to the autonomy, now we might have induced demand. People who increased accessibility, people who were not able to ride earlier now riding, so there's more demand on the network. There's a potential for increased ride-hailing type services because these are going to be cheaper and more convenient. And it might be also called urban sprawl, which should also lead to induced demand. Right? So then the question is, how can cities utilize these new modes of mobility in a way that's more scalable and sustainable? Right? Because technology is not the problem here, right? It's how we're using the technology. So technology should have a positive role to play as well. So three things that we can look at is, well, first of all, enabling and encouraging high capacity ride sharing. So when you take one of these vehicles, don't ride alone, ride with other people. So Uber Pool and microtrans shuttle systems that are starting to gain a lot of attention in the US with transit agencies is one option. Improved utilization of mass transit through things like first last mile shuttles. So we saw that in a couple of talks yesterday as well. And Monica's talk just before this. And finally, this idea of coming up with completely new hybrid public transit systems, again, which we've seen a little bit in previous talks in this workshop. So I'm going to try to give you some background on all three of these types of solutions, starting with high capacity ride sharing. So what is high capacity ride sharing? You can think of it as an app-based system where you go on your app and request a ride. But instead of getting a taxi trip from A to B, now you might be required to share this with someone else. Now, from the system's perspective, what's going on? So I'm going to talk through this setup using a toy example. So in this toy example, there are two vehicles. Vehicle one already has a passenger on board. The inverted triangle is showing the drop-off point. And then there are 4 requests, 1, 2, 3, and 4 with the origin and destination. And there's a second vehicle that is empty. Now, in commercial ride-sharing systems, what typically happens is that these requests, when they come in, so the passengers, are aggregated over some fixed time intervals. This could be anywhere between, let's say, 2 to 30 seconds. In some cases, maybe even lower than that. Now, the longer you aggregate for, the more information your optimization problem has, and therefore the better solutions you're able to achieve. But of course, the limitation is then whoever makes the request on the app has to wait for that many seconds at least to get a response to their request, right? So there's some sweet spot to be achieved there. But most commercial systems are in this range. And I'm going to talk about a framework for solving this real-time high-capacity ride-sharing problem. We don't know obviously what companies are doing in-house, but we have anecdotal evidence at least to suggest that what they are doing, the frameworks they are using are similar to what I'm going to talk about. And just one example, there's a reference here to a talk by the chief data scientist at VIA, which is the largest on-demand transit system company that provides on-demand transit systems. Okay, so how does one go about solving this kind of problem in real time? So like I said, I'm going to talk about one framework for doing this. So the first step in this framework is to create what's called a shareability network. So shareability network or shareability graph is simply a graph with the following characteristics. Each node in the graph corresponds to either a request or a vehicle. So in this case, there are 4 nodes corresponding to requests 1, 2, 3, and 4. And there are 2 nodes corresponding to vehicles 1 and 2. An edge between 2 nodes represents some form of compatibility. So in this case, an edge between 2 requests, so for example, requests 1 and 2, means that those 2 requests or passengers can share a ride together subject to their individual constraints. And the individual constraints could be things like a maximum waiting time, maximum detour that they are willing to incur due to sharing with each other. And similarly, edge compatibility between a vehicle and a request could be defined by, for example, how much time the person is willing to wait. So if the vehicle is too far away, the vehicle is incompatible with that request. Right? And I want to highlight that these constraints can be user and vehicle specific. Okay. Now, once you create this graph, the next step is to come up with a set of trip configurations. So you can think of this as now, once you have this compatibility graph, creating all the possible ways in which people can share. Now, this graph by itself defines that compatibility for pairs of requests, right? So the fact that an edge exists between two requests, so let's say 1 and 2, by definition means one can share with 2, right? But we also need to now understand, if you're thinking about vehicles with capacities of greater than 2, whether 3 people can share with each other. So once again, if you look at the example graph, you see that 1 can share with 2 and 2 can share with 4 and 4 can share with 1. So it makes sense to ask the question, well, can all 1, 3, and 4, can all 3 of them be on the same vehicle? Right? And the answer is, well, it depends. Right? So the existence of a click or a fully connected subgraph between some set of requests is a necessary condition, because if you cannot share with 2 people out of a group of k, well, you can't share with all k of them, but it's not a sufficient condition. And to check whether the sufficient condition is satisfied, one is required to solve a generalization of a traveling salesman problem. Essentially, we need to figure out whether there is a route that exists that moves all 3 of the passengers subject to all of their constraints. So more formally, this would be a pickup and delivery problem with time windows and capacities, because the vehicle also has a capacity, right? Now, in practice, this requires solving thousands of these generalizations of the traveling salesman problem, because at any given 5 to 30 second interval, there could be hundreds of requests and thousands of feasible ways in which these requests can be configured together. All of these generalized traveling salesman problems can be solved in parallel because they're independent optimization problems. And while these are theoretically hard problems, solving the TSP and these generalizations in practice can be done fairly fast, and especially when the sizes of the instances are small. So if the capacity of the vehicle is 4 or 10, these individual problems are not very hard. Now, there's also a question of, well, how many such feasible configurations might exist? Now, in theory, again, the number of feasible configurations grows exponentially with the capacity of the vehicle. But in practice, because of this system constraints, it's very unlikely, even if you have a 20-seater vehicle, that there are that many people who can share together, unless there are a lot of people with similar origins and destinations all along the same path. So there's some natural pruning of the search space that happens here. Even though that's true, there's still the question of, well, even if out of tens of millions, there are only thousands of trips that are feasible, how do you find those thousands of trips that are feasible? So for that, the one approach one can use is to, again, exploit the hierarchical structure of this compatibility. So for example, as I said earlier, for a trip of size k to be feasible, all the subsets of size k minus 1 have to be feasible by themselves. So what one can do is start with trips of size 1, then build the trips of size 2, but only consider trips of size 3, for which the trips of size 2 are already feasible. And when you go to 3 or 4 or 5, already this list has been pruned down exponentially. So you only have a few different combinations of clicks of size 5 to consider, for example. So there's a natural pruning that happens, and which allows you to build this list very fast. And again, remember, we have a very small computational budget here on the order of 5 to 30 seconds to solve the entire pipeline. And this is just one step of this pipeline. Okay. All right. So the next step is, once we have this set of feasible trip configurations, is to solve an assignment problem to decide which of those feasible trip configurations to activate or pick. So this is done through an integer linear program, and the optimization problem here is in fact fairly trivial. So let me just tell you what the two constraints are. First of all, the objective function could be any linear function of the decision variable. So it could be, for example, minimize the total vehicle miles traveled, minimize the detour incurred by the passengers, minimize some profit maximizing objective for the company, and so on and so forth. The two constraints are simply saying, one, that each vehicle can at most serve one trip. And the second saying that each passenger must either be associated with a trip or it should pay a penalty for not being assigned to any trip, because otherwise the trivial solution would be to not assign any passengers to any trips, any vehicles. Okay. Now, the important thing to note with these types of decompositions is that the ILP that's now solved does not embed the road network. So if you think about the sort of classical definition of the vehicle routing problem, so this is a variant of the online vehicle routing problem, also known as the dial ride problem. It is that the network is not embedded in this ILP, which makes it very efficient to solve. Now, this is still like ILP and it's NP hard to solve it. In particular, it's a set partitioning problem. But again, commercial solvers can solve these types of problems very, very fast. And the number of variables here, once again, limited by the quality of service constraints. So in a real-time ride-sharing type system, those quality of service constraints are fairly tight. And that really makes this problem tractable. Because, so for example, in the case of New York City or Manhattan, at any given 30-second time interval, there are on the order of 3,000 to 5,000 feasible trips, which can be solved extremely fast. One other thing I want to note here is that these types of approaches are related to what's known as branch and price in the operations research literature. And in branch and price, you don't actually, in a first step, do the trip generation. You do the trip generation as part of your optimization problem, as part of your assignment problem. The trips are iteratively generated and added to the problem. And you have this iterative process where you keep solving an assignment while adding new trip configurations until a condition is met that allows you to say that you don't need to add any new trips. Now, this is also a really nice way of looking at these problems and a common approach. But unfortunately, in this problem, the sub-problem that appears in this branch and price process, for those who are familiar with branch and price, is what's known as a net worth maximization version of the price collecting TSP. And this is, again, a problem which is not only hard, NP hard, but also we don't know whether there's even a constant factor approximation algorithm that can run in polynomial time. So this is extremely hard class of problems, and one needs to then, again, come up with heuristics for that step as well. We also can solve the ILP using techniques like randomized rounding, which are extremely fast. And in some recent work we did, we were able to show that you can get some nice approximation guarantees using randomized rounding for this type of problem. If anyone's interested in this, I'm happy to talk more about that later. Okay, so once we go through these steps, what we have is a solution, which is the assignment of requests to vehicles. It's also important to note that at the end of this process, if there are any idle vehicles, that they can be rebalanced to locations which might have future expected demand. Now, when the system is saturated, none of the vehicles are idle, so there is no rebalancing step. But for example, in the middle of the night, if the vehicles are distributed across the city, there could be a lot of rebalancing done to move those vehicles to locations where demand might start appearing during the morning rush hour. Right? Now, another important thing to note is that these kinds of frameworks do accommodate time-dependent travel times. So you can embed the notion of traffic, but it does not allow to model the congestion that is actually caused by the fleet. So traffic in this kind of setting is assumed to be exogenous. So if you're routing maybe 2,000 vehicles in New York City out of hundreds of thousands, you could argue that it does not matter, but this is a limitation of these types of frameworks, and including making the congestion endogenous to the model makes the problem much harder. So just to kind of give a sense of how this kind of system would work, I'm going to show you an example of running the algorithm that I just explained on some real data from New York City. So in New York City, there are about 400 to 450,000 trips that are taken by taxis every week. About 2,000 every day, and about 2,000 active trips at any given time. And in the real world, served by about 13,500 taxis. The question we tried to ask was, well, what would happen if you tried to serve these instead with 1,000 or 2,000 of these on-demand shuttles? Okay. And the simulations that I'm going to show you are on the Manhattan network, where there are about 4,000 nodes and about 10,000 edges. Okay, so I'm going to show you a simulation now. The dots in this simulation, the color corresponds to how many vehicles, how many people are on board the vehicle. The dark blue dots are rebalancing vehicles who are moving without passengers. There are, this particular instance has 1,000 vehicles. The capacity is 10, 7-minute maximum waiting time, 14-minute maximum detour. There are some statistics being computed, like the service rate, average waiting time, average in-car delay, occupancy, and distance traveled by each vehicle. And there's 2 vehicles here that are shown just so how their trajectories are now changing every 30 seconds as the vehicles being routed in real time. And the triangles, the inverted and triangles, and the triangles show the pickup and drop-off points, right? And as you see, the route jumps when you get new allocations of requests to be picked up. Okay, so just to again highlight the value of such a system, I'm going to show another simulation here comparing what happens when you have 2,000 vehicles with capacity 1, capacity 4, and capacity 10. Of course, you see in the capacity 1 case, the in-car delay is 0 because you're taking a taxi. There is no delay induced due to sharing. But the average waiting time decreases as you have higher and higher capacities, even though it's the same number of vehicles. And this is natural. It's because each vehicle has a higher capacity. Your sort of effective fleet size is larger. You're able to do more with the same number of vehicles. So you need to wait less time to get picked up. The service rate, as you can see, also increases as the capacity of the vehicle increases. And somewhat surprisingly, the travel distance decreases. And so when you have these higher capacity vehicles, you are serving much more people through fewer vehicle miles traveled per vehicle, right? And this shows a real improvement, a significant improvement in this ratio between passenger miles traveled and vehicle miles traveled, which is what we would like to do. Okay, so this approach that I talked about, it's really a general framework for the aggregate movement of people and goods. Right? And this is sort of, again, in the theme of what Maria Batara talked about yesterday about having these general modular solution methodologies, where, for example, when a company wants to introduce a new service, then they don't have to come up with a whole new implementation of a completely different framework and system to allow for that new service. So this is very modular. It allows for easy integration of features like allowing people to walk to common pickup points, electric vehicle systems where you have to now incorporate charging, personalization both at the individual level and the vehicle level, so heterogeneous customers and heterogeneous vehicles. It also generalizes to related problems like food delivery, school bus routing, and transit applications. And I'll try to give a couple of quick examples of these different settings. So first of all, with walk and ride, and I guess now you get to see, get some insight into this image that most of you might have seen from the workshop website. So if you can walk and ride, what happens is that the system can tell you to walk to a common pickup point or a pickup point that is convenient for the vehicle that's picking you up. So if you've used a service like Uber Pool or Uber Express Pool, you would have seen that the system asks you to walk to a certain point to get picked up. And this has 2 benefits. One is this the example on the left where 2 people can walk to a common meeting point, and therefore the vehicle needs to only stop once to do the pickup. And also, as in the example on the right, by asking the people to walk to a point, perhaps their request was made on a one-way street that is going from left to right, but now they're going to go from right to left. So you ask them to walk to the one-way street that's going in the opposite direction. And this in itself, for example, in New York City, can save maybe even 10 minutes by just asking them to walk down one street. Right? So this is known as walking and riding. And in this framework, what really changes due to this new model is only the fact that the generalized TSP that's solved to check whether a trip is feasible now goes from being a variant of the TSP to a variant of what's known as the group TSP problem. Now, the group DSP problem, again, is a notoriously hard combinatorial optimization problem to solve. In fact, there are hardness of approximation results for general networks. So one of the projects we are working on right now, led by Juan Carlos Martinez Mori, who's a long-term participant in the IPAM program, is to try and understand whether under specific structural assumptions that relate to road networks and these types of ride-sharing problems, whether we can gain improvements on what's known theoretically about this problem. Another related extension is the notion of EV charging. So we do expect most of these AV fleets in the future to be electric vehicles. And if it's an electric vehicle, of course, now your feasibility of different tip configurations also has to include the vehicle charging constraints, right? So once again, in this framework, the only thing that changes during this workflow is that the generalized DSP now also has to include charging constraints. And of course, after this process is done, let's say it happens every 30 seconds, you have to update a charging schedule. So there's an extra step that happens after solving this optimization problem. So you solve the scheduling and routing problem, you update this charging schedule, you go back and solve the scheduling and routing problem subject to the new charging constraints, and you keep going through this process. Right? So this, of course, requires being able to model the battery discharge and to be able to forecast future vehicle utilization, because you want to have most of your vehicles available during peak demand periods. So knowing when the peak demand periods occur is important in terms of being able to come up with an effective charging schedule. And this is also some work that we've been doing led by Matthew Selzak, who's a PhD student of mine. Okay, so now moving on to the notion of demand responsive public transit. As I mentioned earlier, a lot of cities have really been moving towards trying to use what's known as microtransit. So these on-demand shuttle systems to complement their traditional fixed line transit routes. And these are a couple of examples that are actually operating right now, pre-COVID at least. I want to tell you a little bit about why these problems are harder than the type of problem that I just explained. So again, in this case, if you think of a shuttle now, going back to the example from New York City, this is the shareability graph derived from real data. Even though there are about 450,000 requests in a day in New York City, this shareability graph only has 3,000 to 5,000 feasible trips per problem instance. So every 30 seconds, there are only about 3,000 to 5,000 feasible trips. Whereas if you look at a seemingly much simpler problem in the context of school bus routing, where I have a school with 400 students and a bus capacity of 72, there could be about over 10 million feasible trips in this problem. So it's a significantly harder problem to solve, even though to those who are not familiar with these problems, it might seem like an easy problem. So the main issue here is that, as you can see from the two pictures, the shareability network is too dense, and therefore too many trip configurations are feasible. So in these kinds of problems, you need techniques for pruning the search space. And there are many techniques in the literature for doing this. Again, to sort of showcase what would happen in a school bus routing problem. So again, if you take this particular instance of the problem and you try to run the framework that I just explained, doing some naive pruning of the shareability graph, which is necessary, otherwise solving it over 10 million trips is very slow. Even with some naive pruning, the potential trip list becomes 8.5 million trips, and it takes about 3 hours to solve this. If you do slightly better, more advanced pruning, you can drop the potential trip list to about 4.5 million and solve the problem in 24 minutes. Now, again, you can't solve this in 30 seconds, but this is not the type of problem where you need to solve the problem in 30 seconds because school bus routes are determined maybe once a semester, right? One other nice thing, though, about thinking about this problem in the framework that I described is that, again, we have this additional flexibility. So one particular thing that school districts are, for example, interested in is whether you can complement school buses with shuttles in certain cases to increase the efficiency. Because the biggest cost in school bus operations is the number of buses. And if you can really reduce the number of buses you use at the cost of a few, maybe Uber rides or taxi rides or some shuttle that is cheaper, you can save a lot of money. And in this framework, we can simply add the taxi trips as a feasible trip configuration on top of the more traditional bus trips that are in the system. And you for free, you get these multimodal solutions that tell you the optimal allocation of students across the multiple modes. So this is sort of a class of problems that we are looking at in a practical setting with many transit agencies. So the transit-centric problems, even when they're online, not offline like school bus routing, can still be hard. And that's primarily because the quality of service constraints are much more relaxed and the vehicle capacities can increase. So if you're taking an Uber pool, you're probably not willing to have a detour that's significantly larger than taking a taxi trip. But if you're someone who's taking a bus, your comparison point is not a taxi trip, but your comparison point is how much time it would take for you to make that trip through using the bus, right? So the constraints that are, and the price point that the service is operating is much lower. So the number of feasible trip configurations naturally grows, and it requires these kinds of applying faster techniques to solve it than what I described earlier. So in particular, this is work we are doing with King County Metro in the Seattle area, which is a transit agency that has worked a lot with these types of on-demand shuttles. Also with Minneapolis-St. Paul, where it's an agency that's trying to get into this space that does not have as much experience and will be doing their first pilot using on-demand shuttle, hopefully next year. Those two projects are with Ford and sponsored through a DOE grant. We also have a NSF Smart and Connected Communities project led by Vanderbilt University and the Chattanooga Area Transit Authority, where we're also trying to deploy a pilot program next year to operate these kinds of shuttles to complement their fixed line transit services. Now, to solve these kinds of problems, I said we might need faster approaches than the approach that I just talked about. And one way you can do this is to think about these problems using LP-based approaches as opposed to the ILP-based approach that I talked about. So in an LP-based approach, of course, there are pros and cons. So what is the LP-based approach? So here's one way of thinking about this same problem in an LP-based approach. You could say that at each iteration, that only one new request can be assigned to a shuttle. Right? So in the trip configuration that I talked about, you could have multiple new requests that are being assigned to the same shuttle in the same optimization problem, which leads to this hypergraph matching problem and thus a LP. But if you restrict the fact that if you make the restriction that only one request can be assigned to a vehicle in each iteration of the optimization, then what you get is a regular matching problem, and you can solve this using a LP exactly. Now this leads to a big computational gain. In particular, more so than the gain of solving ILP versus LP, it leads to massive gains because you don't now have to define the full trip configuration list, which is really the computational bottleneck here. So you are able to now solve this problem much faster. Now, of course, what is the limitation? The limitation is that you can't assign multiple people to the same vehicle in the same time window. Right? So if two people come down at Penn Station and need to go to Madison Square Garden for a basketball game, well, you're not going to have to put them in two vehicles just because that's the limitation of the optimization problem. It turns out that you can extend these kinds of methods to have most of the benefits computationally, but not have the drawbacks in terms of quality of solution. And there's a lot of, I think, interesting research area in exploring these kinds of methods that we are very interested in. Another important extension in the context of transit applications is that of understanding that these types of solutions are myopic. So they're myopic in the sense that at any given time window, you're not considering the future demands. You're only solving this optimization problem with respect to what's in the system at that point. And in systems like ride sharing, where these vehicles are fairly saturated, this doesn't hurt that much. Of course, having future information can help, but it doesn't hurt too much. But in more transit type applications where there's a lot of capacity in the vehicle, and if you route it along the right corridor, you may be able to pick up other passengers at a lower cost. This type of looking at this problem in a non-myopic way tends to be really useful. So this is, I would say, sort of these type of approaches are being used in the setting of taxis, where there's a single capacity vehicles, but there's not a lot of literature out on incorporating future information into these shuttle systems. Finally, I want to talk about this notion of a hybrid transit system and how one could envision transit systems changing with all of these new technologies. So in transit planning, it's been known for a long time that if you want to maximize ridership, that you should operate a few routes at very high frequency. So to kind of showcase this idea, I'm going to use an example from Jarrett Walker's blog. So Jarrett Walker is a very famous transit planning consultant. So you have this case of maximum ridership on the left, where there are these buses that are assigned to two lines. And if you can see these gray dots on that map, that corresponds to the demand. So you can see that along those two routes are where most of the demand is. And if you assign all of your buses along those two routes, you maximize your ridership. On the right-hand side, you have an example of maximizing coverage, where now the buses are spread out. So more people have access to a bus. The bus goes closer to more people. But now the frequencies of the buses, since they're spread out, is much lower, and there are higher headways, so fewer people take the bus. So there is less ridership. So there's a trade-off here between ridership and coverage implying, again, equity. Public transit being a public service, of course, is not just trying to maximize ridership, but it's trying to provide equitable services. And this is something that's happening a lot in US cities, this move from more coverage-based routes to increasing the number of buses that are being operated in ridership-based routes. And Houston was sort of the poster child for this movement. In 2015, they flipped the switch and increased the number of ridership-based routes from 55% to 80%. And of course, this led to an increase in ridership, but there's a question about what that means in terms of coverage. And one idea is, of course, whether you can use these types of new technologies to maybe get the best of both worlds, increase ridership by not compromising on coverage, by using more dynamic services, as has been alluded to in previous talks, to cover the coverage routes. Since I'm a bit low on time, I'm gonna maybe go through this very quickly. Line planning is a well-known problem and a very hard optimization problem, where you're trying to find the best fixed transit lines for a network. In our context, we have this notion of a hybrid system where now some of the lines are fixed and operating at very high frequency, but you're also designing what those fixed lines are in the context of knowing that there is a complementary service that can dynamically move the remaining passengers, right? So this is different from the classical line planning problem where the lines are designed to serve everyone, whereas here the lines are designed to serve some people, and knowing that you have a complementary service that can serve both as a first last mile connecting service and as an end-to-end service. And there are a number of very interesting and very hard optimization problems in the context of these kinds of problems. Finally, one other thing that I think autonomous systems can help transit services with, in microtransit, one of the biggest problems is that driver labor and the related time-based costs are a dominant element of operational costs, right? So about 70% of more, according to some studies. Now, if you have a big bus that is 50, 70-seater, and you replace it with 5 shuttles because they can be more agile, well, in this context, your cost is going to be 5 times as much, almost, because now you have 5 operators in those shuttles. So if you breaking down the bus into smaller pieces is good as long as it doesn't cost more, right? And this really, again, it highlights the importance of these modular systems that Monica just talked about. Right? So if there was a way to break down the bus into pieces without having to pay for 5 operators, that would make these kinds of microtransit systems even more viable. And of course, this is happening to some extent already because TNCs, transportation network companies, operate at a lower cost than transit agencies because of the different labor laws they have to operate under. So currently, most microtransit pilots that are successfully operated by transit agencies are those where the first last mile connector is operated by a third-party TNC contractor who is much cheaper to operate than the transit agency internally running their own microtransit service. Now, with the advent of autonomous shuttles, this kind of equation changes, the economics changes, and these kinds of systems become even more economically viable. I will close by saying that transportation is really a critical infrastructure system, and public transit is an essential component of this. That in this kind of age of innovation in emerging mobility technologies has to some extent been left behind. So I'm really excited to see that we saw a bunch of talks during this workshop that are trying to bring transit back to the fore, as Pascal said yesterday, to make transit cool. So that's really encouraging. A lot of the technologies so far have not really benefited public transit and the sort of communities that rely on public transit. So I think we also need to find ways to invest more in R&D for public transit related systems, because public transit doesn't have the same amount of VC backing, for example, that ride sharing companies have. So I think and agencies and researchers need to think about also public policy and regulatory measures that can help encourage transit use. I would like to thank, of course, the many collaborators who have made this work possible, and the funding agencies and both the industry and public sector partners. Thank you.